Well, thanks very much, Ian. Okay, so what I'm going to talk about today is joint work with Martin Breitson, and some of it is joint work with Martin and Henry Walton. So certainly it's been an ongoing project with Martin that we've been trying to understand this idea of profinite rigidity and flexibility. So let me start in a much more mundane version without muttering the word profinite here. So all groups in town, so gamma, if it's a group, it's always finitely generated. Okay, so gamma is always going to be finitely generated. And I'm always going to assume that it's residually finite. And residually finite. So just to recall what that means, it means the following. If we've got G is an element of gamma and it's non-trivial, then to be residually finite means that we can find out a homomorphism, say Q, down to some finite group A, for which Q of G is different from the identity. And the reason for looking at residually finite groups is that they come with a large collection of finite quotients. So that's what I really care about, groups that have got large collections of finite quotients. As you'll see later, it's easy just to stick on free products with infinite simple groups, and everything I say is just complete nonsense. So it's good to stick within the class of residually finite groups. Okay, so the good news is that there's lots of residually finite groups. So there's lots of RF groups. So for example, finitely generated subgroups of GLNC. And thanks to Perlman, the fundamental groups of compact three manifolds. So Perlman.
So GLNC is finally generated residually finite.
What's that? So thanks to Perlman and an argument of Thurston and Hempel, pi1 of a compact three manifold is residually finite. So there are lots of finitely generated groups that satisfy the property of being residually finite, and certainly all the groups that occupy my office either here at the Institute or in Austin are residually finite usually. Okay. So what's the question here? So the basic question can be stated really in a very pedestrian way. So the motivating question is the following, and maybe let's just state it like this. So let's let, for a group gamma, so let's let the C of gamma just to be the set of finite quotients of gamma. So maybe thinking of isomorphism classes where A is a finite quotient of gamma. Okay, so again, let me just be clear here. So at the outset here, here's the group gamma. A could be the alternating group on 17 elements. Okay, if there's an epimorphism from gamma to the alternating group on 17 elements, then I put that on the list. I don't care if there's 1,000 different epimorphisms from the group gamma to the alternating group on 70 letters. It just goes in the list. It just gets included there. Okay, so there's no multiplicity or anything. So the motivating question is this. Let's call it question 1. To what extent does this collection C of gamma determine gamma, again, up to isomorphism? Okay, so that's the basic question that motivates a lot of what Martin and I have been thinking about with regards to this kinds of ideas. And so let me just say a few things about, positive answer. Okay, so the first group that you might think about is, well, can you detect the infinite cyclic group by its finite quotients? And the good news is yes. So if gamma is Z, then C of gamma is just equal to gamma. And why is that? You may wonder. Well, it's a simple exercise, but let's just talk ourselves through it. And so the point is, if we've got a fake guy, so if there was delta with C of delta being C of gamma, the same finite quotients, well, all the finite quotients here are finite cyclic. Okay. Now, there's two possibilities here. Let's just think about this. Well, we could be in the situation that delta was non-abelian. Okay, so case one. Oh, yeah. So of course, this is my standard mistake here. So let me just. Okay, so let me make another definition over here. So there's going to be lots of bad notation through the talk. So this is the first one. So let's define the genus of gamma. And this is not our notation. So the genus of gamma is the collection of those guys delta in finitely generated residually finite groups such that C of delta is equal to C of gamma. Now, why is it called the genus, you might wonder? It's got nothing to do with surfaces, but it's coming from the theory of quadratic forms over Z. So the genus of a quadratic form over Z are things when you're locally equivalent for all primes P and equivalent over the reals, but you may not be equivalent globally over Q or Z. So that's kind of what's happening here. We're trying to understand kind of the local picture, i.e. the finite quotients, and trying to recover the global picture, i.e. the full group gamma. So that's really where the word genus comes from here. So here, I'm just saying that the genus of the infinite cyclic group is the infinite cyclic group. Okay, so case one, we could be that delta is non-abelian. But a moment's thought then says that, well, we just choose a non-trivial commutator. So we choose C to be a non-trivial commutator. Well, we're meant to be residually finite, so there's meant to be a finite quotient that doesn't kill C. But that's illegal, because all finite quotients here are abelian. Okay, however, RF and cyclic quotients give contradiction. So case two now, delta is a finitely generated abelian group. Well, in this case, the structure theory of such things tells you that, well, okay, the only possible thing you could see here is the infinite cyclic group. Why? Well, if you did anything else, you could construct a finite quotient that was more than just a finite cyclic group. Okay, so again, you get a contradiction from the structure theory of finitely generated abelian groups. So that's the good news. Z, and in fact, this argument can be modified to show that finitely generated abelian groups are the same holds for finitely generated abelian groups. But then, after that, things get a tad more exciting. And, by and large, this is basically the only example that I could tell you without thinking that, these are determined by their finite quotients. Now, this is completely elementary, but what's that? Well, I'm just coming to that. So, in fact, there's an example of Baumslag that says that you do not have to go very far. In particular, it'll be nilpotent groups, for which they're just going to be a very simple extension of Z, and they're going to be non-isomorphic, but they'll have the same finite quotient. So there's an example of Baumslag that gives a pair of groups, gamma 1. They're an extension of Z. Now, there are various finite cyclic groups that go in here. There's some numerology that one has to be careful about, although not too careful. For example, we could put 11 there, and this will work. We have gamma 2. So these are not isomorphic, but what Baumslag shows is that, in fact, these do have the same finite quotient. So in fact, just moving a little bit beyond the infinite cyclic group gives you some interesting classes of examples. And as Zev was pointing out, somehow nilpotent groups will be the next thing you think about. Well, there's a nilpotent group that makes life a little bit more complicated. But more generally, kind of the structure of nilpotent groups that lie in the same genus is fairly well understood. So there was a student of Baumslag, and I just like to say the name, Pickle, that kind of really understood the nilpotent case. So kind of understands G of gamma when gamma is nilpotent. And in particular, he constructs examples for which G of gamma has cardinality bigger than 1, but it's always finite. You can make it arbitrarily large, but it's finite. So you can make always finite. Okay, so there's already some complexity in the world of nilpotent groups. So again, from my perspective, perhaps lattices and semi-simple Lie groups are things that are more natural around my house than nilpotent groups. But and that's kind of where I'm going to get to with Kleinian groups. But just to make the remark here that there are examples, and these were constructed by Miniaka, who's a former student of Alex Lubotsky. Let me just kind of say here gives examples of lattices in certain semi-simple Lie groups with this genus being bigger than 1. And again, the comment I made here, and so what's built into here. Yeah, indeed. Exactly. So the kind of situation that is good here, that kind of mimics kind of what's going on here, is when one can say something about constructing groups with the same finite quotients. There's always, at least in these kind of situations here, there's number theory controlling the finite quotient. So here, one has to appeal to things like the congruent subgroup property to organize all the finite quotients. There's more that's needed, but that's kind of one of the key ingredients. So you need something like the CSP. Okay, so what about 3 manifolds?
And again, any this class number, I call it this finite.
In these cases, yes, exactly right. Now, there are examples that were constructed for which this genus can be made infinite, but not in this kind of situation. Congruent subgroup property. So let me do the basic version. I can do the basic version, but I'm not going to go much beyond the basic version. Okay, so if you think of taking SLNZ, then for any n bigger than or equal to 2, there's some natural quotients that God gives you. Okay, so it's just SLNZ mod MZ, and then what's called the kernel of that epimorphism to be the principal congruent subgroup of level n, level m. So a group is called congruence if it fits into here. So, and then this guy has the congruent subgroup property if every finite index subgroup looks like this, i.e. you can find some guy like this that's a subgroup of finite index. So, so for n bigger than or equal to 3, this turns out to be true, and this is kind of one of the dichotomies between SLN. Yeah. So n bigger than or equal to 3 has this property, i.e. every finite index subgroup fits in as I've described it there, but SL2 does not. And there's kind of souped up versions of that one can use here. So compact 3 manifolds. So you may be tempted to just think about saying that maybe they should be distinguished by their finite quotients, but of course, once you kind of see things like this, it gives you pause. And in fact, Louis Funard constructed examples of closed geometric 3 manifolds. So these examples were modeled on solved geometry. Let's say 3 manifolds, say M1 and M2, with their fundamental groups having the same finite quotients. And once again, as Peter was alluding to, when you start to enumerate examples where the genus can be made bigger than 1, then there's kind of class number stuff kicks in that gives you large numbers, again finite, of these solved manifolds that have the same finite quotients, but they turn out to be non-homeomorphic. And more recently, Hempel also gave examples of certain Seifert fibered spaces. So already the world of 3 manifolds is kind of interesting. There are examples where one cannot detect the group by finite quotients. On the other hand, there's a very yeah, these were closed. He gave closed examples that were modeling H2 cross R, and he gave examples that were with boundary as well. So the one with boundaries are perhaps less interesting, but these guys are modeling H2 cross R. That's kind of the thing. I mean, the way that it's stated is just in terms of finite quotient of the group. But there's a very nice paper of Henry Wilton and Zaleski that it shows that the geometry can be detected by finite quotients. So they proved the following thing, and this makes heavy use of the recent work of Egel and Wise that I'll be using shortly. Let's suppose that M is closed hyperbolic 3 manifold, and N a closed 3 manifold with the property that that the finite quotients of M are the same, the fundamental group of M is the same as the fundamental group of N with that statement that pi 1 of N at least has the same finite quotients. Well, you would like to prove that N is M. One can't do that just yet, but one can prove that N has to be hyperbolic. Okay, so it's like a geometrization using finite quotient. So N is at least hyperbolic. And I'll come back and make a comment on this shortly. So, finite quotients kind of see the geometry here, which is already kind of an interesting statement. Okay, so this gets me to what I really want to talk about today. What's the situation for finite volume hyperbolic 3 manifolds? So today, I just want to focus on certain finite volume hyperbolic 3 manifolds. Okay, and again, I'm going to focus on not this initial question here, wherever it's going, here, but only restrict to groups within the world of compact 3 manifolds. So we're only going to be considering identifying M, again, as above here, let's just say finite vol hyperbolic by its finite quotients amongst compact 3 manifolds. Okay, so that's what I'm going to talk about. Now, let me just provide a cautionary tale. Okay, so back here, we went Z, and then we went to this example of bound-like, i.e. nilpotent things. Well, if it were free-thinking people, then we would go to the free group of rank 2 as the next generalization of Z. And there, it's still an open question. So this is, in some sense, what motivated Martin and myself. So an open question still. If gamma is equal to the free group and bigger than or equal to 2, is the genus of gamma equal to gamma? Okay, so this is kind of amazing when you think about it. That okay, we know what all the finite quotients are of the free group of rank n. Okay, it's all finite groups that can be generated by at most n elements. So you think, okay, that's a way of organizing finite quotients in the kind of the way that I was talking about number theory organizing things there. However, it seems to be a theme that's emerging that somehow free groups are just fantastically complicated. And even though one can state in words what all the finite quotients look like, organizing that in a useful way is kind of hard. And that's kind of the theme that's come out of Ian's work and Danny Wise's work, that somehow this Lerf property in the context of hyperbolic manifolds is a powerful thing, and it may well imply, if I was a betting man or a man that might be, bought a drink in the evening, I would certainly say that that's a true statement, and indeed, perhaps even say that. Let me just state it brazenly, even though it's on video now for forevermore, that if gamma, I'm only speaking for myself here. I don't know about Brightson, but I'm going to say yes to that. And more generally, if gamma is pi1 of finite volume hyperbolic, then answer is also yes. Now, this is a wee bit ambitious, given that if we're going to do that, almost surely one has to be able to answer the free group question first, for reasons that will become clearer in a few minutes. Okay, so.
So this is only among.
No. I'm going to just be bold here. I'm just going to say, amongst all finitely generated residually finite groups. Now, what you said, I think there's a deal more evidence that might well be true, and we'll maybe talk a little bit more about that shortly. But I'm just going to be bold and state that. Okay, so I think I'm ready to state a theorem.
What about hyperbolic cumulative groups?
Right, so that may well be the theme that, I'm not going to get that ambitious, but I think that's kind of the thing. This virtually special groups might well be good candidates again for guys that are determined by their finite quotients. But I'm not going to be that bold, Jeremy.
In the closed case, so are all the groups in the genus of a closed hyperbolic three manifold groups a group also three manifold groups?
Well, so here we've assumed that it's a closed three manifold, and so to get that statement, you need closed three manifold. Okay.
But there might be groups.
So there could.
Not three manifold.
Okay, so there could. These fake examples in the same way that there could be these fake free groups, okay, that have the same. So there could be this fake free group of rank 2. So what might that look like? Well, it's this 100 generator group, and all you can ever see are 2 generator quotients, or up to 2 generator quotients. Now, maybe that's plausible, maybe it isn't, but it's definitely a challenge to exclude that possibility.
I assume your problems all come when you reconstruct the group from this information, not just that you need.
Well, that.
The proofs, when they, if you show us the theorem, it will show us how to reconstruct, right?
Well, it's a little mysterious because it goes through one of the words, the title, the profinite completion. But that's what's going to be reconstructed here. And then in that case, it's going to say they're rigid.
By the way, in the higher rank case, it's much worse than you mitigated it. You can have a maximal subgroup of SL3Z, maximal proper infinite index subgroup, which is profinitely distinguished.
Right, exactly,
itself. So
exactly.
You just have a finite group in a context.
Right.
Infinite index.
Right. So, and again, as Peter's alluding to things that in this world, because of Lerf, those kinds of finitely generated subgroups don't show up in things like finite volume hyperbolic three manifolds. Okay, so let me state the theorem here. So this is with Brightson. And Wilton. And it's a fairly modest theorem, but it's kind of interesting. It uses some of the ideas that I've talked about. So let's consider the following kinds of examples. So let's let M be a one-punctured torus bundle over S1, which is hyperbolic. And again, so what does that mean? It means that we've got a manifold that's constructed as the mapping torus of some. So here's T2 cross I, puncture T2 cross I, and we glue top to bottom by some map theta, and theta is going to be a pseudo-nocive map. And I'm only ever going to talk about orientable things. So theta here will be an element of SL2Z, and it's because I'm talking about hyperbolic things, theta is going to be a hyperbolic element of SL2Z. Okay, so then let's let N be a compact 3 manifold with fundamental group that has the same finite quotients as pi 1 of N, with the fundamental group of N having the same finite quotients as the fundamental group of N. Okay, so then I'm going to write down something it's not quite true, but I'm going to blur notation, right? So I'm going to say that M is homeomorphic to N. Well, the way that it's been written, M is not actually N's a non-compact manifold because it's a once-punctured torus bundle over the circle. So maybe if I was being careful, I would put the interior of N here. Okay, so it's just a matter of convention of including the boundary or not. But anyway, so M is homeomorphic to N. Okay, i.e. we can determine once-punctured torus bundles that are hyperbolic by their finite quotients amongst compact 3 manifolds. So let me just make a remark. So this was proved by Martin and myself in the case of the figure 8 knot. In the figure 8 knot complement, so it's a particular example of a once-punctured torus bundle with everybody's favorite monodromy. And this was also shown independently using slightly different techniques by Michel Boileau and Stefan Friedel. But their techniques don't actually handle the case that I've written down here. Okay, so I want to talk about some of the ideas in the proof of this and at least indicate why kind of the recent work of Egel and Wise has actually been very important in trying to organize these questions to do with finite quotients. Okay, so let's set up some notation here. So let's just have a blanket assumption that all manifolds in the universe are orientable. All manifolds. This is just a convenience. Otherwise, I have to say some more words. So all manifolds are orientable, and I'll let gamma be the fundamental group of M, and delta be the fundamental group of N. Now notice that gamma and delta have got the same finite quotients. Gamma is this fundamental group of this finite volume hyperbolic manifolds. In particular, it's infinite, and it's got lots of non-abelian finite quotients that come from this faithful discrete representation into PSL2Z. So in particular, delta, we know it's a fundamental group of a compact 3 manifold. It's residually finite. It's going to be infinite and going to have lots of finite non-abelian quotients just because it has the same finite quotients as gamma. So delta is infinite and has lots of non-abelian finite quotients. Okay, so let me make a remark and a reduction that you may think is actually progress. But in fact, it's an illusion, although to get to this point involves some significant bits of math. Okay, so let's put it in color. Probably red, because there should be a warning here. Anyway, there's no. Oh, here we go. Reduction. Okay, so again, let's think about what M is. So M is this sort of finite volume hyperbolic three-manifold. It's a once-punctured torus bundle. So it looks like the interior of a manifold that's compact with a single incompressible torus boundary component. Okay, so let's assume this reduction here that N is a compact, irreducible. So every embedded two-sphere bounds a three-ball, irreducible three-manifold with incompressible T2 boundary. So it has a unique boundary component, it's a torus, and it's incompressible. Now, you think, golly, that seems like you're almost done, but in fact, this is just where the excitement starts. But let me make a couple of comments on how one would get this far. So getting to this point. So you may well ask yourself, well, why in God's green earth could, here's M. It's got this torus boundary component. So why couldn't there be this closed three-manifold with the same finite quotients as pi1 of M, so as gamma? So why can't delta equal pi1 of a closed three-manifold? Well, it can't be, and the only reason I know that it can't be is thanks to work, or a consequence of work of Agel and Wise. And why is that? Well, so if you think about it again very naively for a minute, here's this guy gamma. It has a z cross z subgroup that comes from the boundary torus. Now, I've assumed that, pi1 of this closed three-manifold. Well, okay. Why couldn't, maybe there's no z cross z in here, but there's a z cross z in this, in this other guy. I mean, why is that seen? Why is this z cross z seen at the level of finite quotient? So that's the kind of thing that Wilton and Zaleski kind of had to handle here, that they were assuming you had a closed hyperbolic guy with the same finite quotients as this guy N. Well, N could have had a non-trivial JSJ decomposition. You have to see that z cross z by finite quotients. Now, when I say this every talk I give, and at some point somebody's going to say it's obvious, but as far as I can tell, this needs the full power of Agel and Wise. Okay, and why is that? Well, you can. Maybe it's too early to say this, I should really talk about it later. But anyway, somehow what can be seen as cohomological dimension. So that's what can be seen using finite quotients. And that's what can be organized using Agel and Wise's work, that manifolds are virtually fibers. So there's a kind of a bit of a story that goes in there. For those that know the words, these groups turn out to be good in the sense of Ser, and that's what can be used to do that. So, I mean, I wish that somebody would really tell me that, Alan, you're an idiot. Well, people tell me that all the time, but in this particular case here, that there's obviously a way of seeing the Z cross Z subgroup.
Do you need virtual fibrin or virtual specialness?
Virtual fibrin would be the cleanest way to do it, but in fact, just having the quasi-convex hierarchy in LERF would be enough to do it. Okay, so that's one thing.
They're all theorem of Lubotsky, which shows that convoluted subgroup property fails.
That's true.
Is not enough. So he did
right.
answer some questions without understanding.
Right, but you need more than you need more than what he does. But you're okay. So that's one thing that's kind of buried in here. And then another thing that's buried, you might think, well, why couldn't it be a connect sum? Why couldn't this N? So why can't N be a connect sum? Okay, so again, we're just talking about finite quotients. So you've got this free product picture. I mean, why? How can you see that through finite quotients? Well, it is true again that one can do that, but in fact, the only way I think that I know how to do that is using, again, something more sophisticated. Again, I wish somebody would tell me there's a slick way, but this uses L2 Betty numbers. It uses the L2 Betti number, and this is work of Lott and Luke. It kind of says that if you've got this finite volume hyperbolic three manifold, the first L2 Betti number is 0. If you reconnect some, it's non-zero, and then the first L2 Betti number turns out to be an invariant of having the same finite quotients that is not obvious at this point, but maybe will be somewhat more obvious later. Okay, so there are these little things that are quite substantial to prove that are needed to get to this point here. Okay, so but let's assume we're at this point here. As I said, that's where really the excitement does start, and then see how far we can go. The L2 Betti number. Yeah, so you know, it's certainly a true. It's a true statement that you know, abelianizations are the same when you've got the same finite quotients. But you need more than that here. Okay, so now let me talk about the plan of the proof. Okay, so we've now got that. We're now got to this point where n is this compact irreducible three-manifold with incompressible torus boundary, and as I just mentioned, again going back to the argument I gave right at the start of the day, that the same finite quotients means that you know these homology groups are the same. So that's an invariant of the same finite quotients. It's just the same as I was talking about earlier. Now, just as a comment here, so M is a once punctured torus bundle. So what does that look like? So M looks like, let's just write it like this, M phi for some monodromy phi. And so what the fundamental group, or gamma, looks like, it looks like there's this stable letter T together with generators of the free group, that's the fiber, and they're subject to the relations that T inverse is given by the action of A, and then there's the action of B that gives you T inverse. So in particular, you know, the torsion of this H1 is fairly limited. Okay, it's at worst a 3-generator group, and so at worst the torsion is going to be cyclic or have rank 2. So it's a very simple piece of homology here. Okay, so the torsion here is very limited. And in particular, if you think about this for a minute or two, we're assuming that we're in a case where you know theta is a hyperbolic element of SL2Z. So what do those mapping tori look like? Well, if you think about the action on homology, if you abelianize this and look at the presentation matrix, that gives you some little matrix, a 2x2 matrix, for which you can work out what the homology is. So in the case when you know theta is hyperbolic, then it turns out to be the case that if you look at the first Betti number of these mapping tori that you get by taking powers of theta, then this is always 1. Okay. And this kind of picks out those hyperbolic elements inside SL2Z, that the first Betti number of the associated bundle is always 1, if and only if it's a hyperbolic element. Now you're going to say to me, well, wait a minute, what about something that's periodic? Okay, so you take this element of order 6 in SL2Z. Well, the 6th power of that's the identity. So that acts trivial in homology. So there's a finite cover for which you see Z cross Z cross Z. So, and then if you've got trace 2, you always see rank 2 homology in finite cover. So this you know, picks out hyperbolic once punctured torus bundles. Okay, so that's useful for what we're going to say later. Okay, here's the plan. So part 1. Let's prove that the manifold N is fibered. Okay, so part 1. So prove that N is fibered with fiber a once punctured torus. So this is really in the work that Martin and I did, that what we're really saying here is that you can, in the case when it's rank 1 homology, B1 is 1, and there's non-empty boundary, although I think now we can do better than that, that being fibered is an invariant of having the same finite quotients. So being fibered so this is in the case when, let's say, boundary of M non-empty and B1 of M is 1. Okay, so now you get to this part. Okay, you've assumed, you've proven that N is fibered and the fiber is a once punctured torus. Okay, so now we go back over here and we think about what the possibilities are. Okay, well the possibilities are that that guy N there has the same first homology as M, and in fact that's true in all these finite cyclic covers. So again, it's a nice fact about once punctured torus bundles that if we have phi in SL2Z and we look at let's say hyperbolic, the order of the torsion is given by the absolute value of trace of phi minus 2. So what's the point here? Well, the point is this reduces you to, once you know the fibers are once punctured torus, so this reduces you to a finite number of possibilities. Exactly. Exactly. As Peter was saying, because you're now reduced to this kind of trace statement, there's only finitely many conjugacy guys of a given trace in SL2Z, and that reduces you to understanding these finite number. Now this is basically where Brightson and I got to before. So at this point you can handle the figure 8 knot. And why is that? Well, in the case of a figure 8 knot, H1 is just infinite cyclic. There is no torsion in that case. And the monodromy for the figure 8 knot is the one that everybody writes down, is that, i.e. the trace is 3. Okay, so one will notice that 3 minus 2, that's 1. Now what's the only other possibility here? Well, 1. Okay. Now what's 1? What does that correspond to? It corresponds to a periodic element, and it's the trefoil knot complement. Now there are various ways to eliminate the fact that the figure 8 knot and the trefoil can have the same finite quotients. You don't need any sophistication, but that's kind of where you get to at this point. Okay, so it's the only hyperbolic once punctured torus bundle with H1 being infinite cyclic. Okay, so then one has to do something else to do this, so we need sort of new techniques. And this new techniques, we'll see how far we get here. This involves a positive solution for the congruent subgroup property for SL2Z, thought of as the outer automorphism group of F2, as the mapping class group of the once punctured torus. So this uses CSP, and it uses something called omnipotence. Omnipotence. So yeah. So this is, again, as I said earlier, there's some pretty awful notation in this talk. That's not due to me. I'm not even sure if it's due to Wise, but I'm going to blame him. So that's where it's first in a paper of Danny Wise. But so maybe we'll get to this point, or maybe we won't. We'll see how it goes.
Tell us what this congruent subgroup property.
I will do. Okay. So that's the plan. So how do we organize things? Okay, I still haven't muttered the word that I probably should have done if I was an adult, profinite. So the way that one organizes these finite quotients is via the profinite completion.
Sorry, Alan.
Sure.
Is there ever an explicit place where you get that and so after step
it's easy to rule a hyperbolic. It's easy to rule non-hyperbolic, basically for these kinds of arguments here. That exactly. So you look at some finite sheeted cover. If it's non-hyperbolic, there's always a bundle that's got, a cyclic cover that's got rank of homology at least 2, for example, and that's not the case for the monodromies that are pseudo-Nosov.
So you didn't actually need to worry about the trefoil then?
I didn't actually need to worry about the trefoil, but it's good to just say it here because it's, it's the only other possibility. That's right. Okay, so organizing finite quotients. Okay, so the way to do this is via the profinite completion. So if we've got our group gamma finitely generated, one doesn't need residually finite here, but we can just assume that it is for the sake of it. Let's let n be, let's just say, the set of normal subgroups of finite index in gamma. So finite index in gamma. Well, this can be turned into an inverse system using kind of reverse inclusion of subgroups, and the profinite completion is just the inverse limit of gamma mod n and n. Okay, so if you haven't really seen this before or thought about it for a while, it's just kind of a mystery. And the good news is, you've organized it. It's a compact Hausdorff, totally disconnected topological space. On the other hand, it's a compact Hausdorff, totally disconnected topological space. So, you may wonder why that's actually good, but in fact, it's a very powerful tool. There's a whole real theory of profinite group theory that really mimics, in many cases, the discrete world and can be used in many cases to show differences in the discrete world. So maybe one thing to say is this can also be identified with the following thing. So if we give, so equivalently, so you can think of this, gamma hat guy is living inside the product of all of these finite quotients. If we give these finite quotients a discrete topology, we get compact discrete spaces. And so we can think of sending gamma to the product gamma mod n, where n is in n. Let's just say, let's call it map J. And the map J sends an element to, let's just say, left cosets by normal subgroups. So it's this giant kind of vector, because you're in the profinite completion, then there's maps between various things. And what we do here is just take the closure of that. So let's then, what happens is that the profinite completion of gamma is identified with the closure of that subspace there. So I don't know if that helps or not, but anyway, that's kind of what one has in place, and it's a very powerful tool to help organize finite quotients. And the reason it's powerful is the beautiful key fact that, in fact, the statements that I've been making about finite quotients is just a statement about the isomorphism class of the profinite completion. So if and only if we have that gamma 1 hat is isomorphic to gamma 2 hat. So again, let's just say finitely generated, residually finite if you want, then this, having the same finite quotients, is the same as being the isomorphic profinite completion. Now, when Labus told me this, I was kind of amazed. Okay, I just thought, well, how can that be? Because I've just started off with a set of finite quotients. There doesn't seem to be any structure there. But once he yelled at me enough times, I began to understand why it was true. Yeah. Well, yeah. Well, I'm sure he says it better than I. He has more practice. So this way is pretty straightforward. This way is kind of the hard way, that going from the same finite quotients, that you really can recover the structure of the profinite completion. Okay, so this is the key thing. And then just maybe one thing for the experts. If you go back and look at the old papers where this is first proved, and in the book by Ribbs and Zaleski, they'll be talking about topological isomorphisms. But thanks to work of Nikolov and Siegel, you can just think of this now as an abstract isomorphism, because all maps are continuous. Okay, so then the statement of C gamma 1 equals C gamma 2 implies gamma 1 isomorphic to 2. This is now the same as this having the same profinite completions, and that's where the term profinite rigidity comes from in the title. So we want to kind of prove now that these once-punctured torus bundles are profinitely rigid amongst the collection of fundamental groups of compact three manifolds. Okay, so let me comment on one.
Alan, can you give like one example that you would mind of
Z-hat.
Oh,
Sure.
is Z hat? I mean, you know, my advice is don't think about it. Okay, that's my advice. You know, don't think too hard about it. You know, I think that's one of the things you learn. You know, as somebody who comes from a geometric background, you try to think about, well, what's the geometry of the profinite completion? And you may as well just stop, because somehow all of that intuition goes out the window. So for example, if you take the profinite completion of a free group, okay, there's copies of surface groups, abstract surface groups of all genus, living inside the profinite completion of a free group. Now that freaks you out. It certainly freaks me out anyway, but so it's a very complicated object. Okay, so some comments on one. Okay, so let's assume that so let's assume, in fact, that we've got a guy that's fibered, and then deduce, in fact, that the fiber then has to be a once-punctured torus. So this kind of illustrates what I was saying earlier, that to solve the general question as to whether three manifold groups are profinitely rigid, one really needs to answer the question about the free groups to begin with. So let's assume we've proven that n is fibered, and then show that n is a once-punctured torus bundle. Okay, so gamma, that's our once-punctured torus bundle. It has the structure, as we remarked earlier, of this extension of the free group of rank 2. So F is the free group of rank 2. Now, by residual finiteness, I mean this map here that I wrote down, it's injective. Okay, so gamma embeds inside its profinite completion. And one gets a sequence that looks like this. Now, you're tempted to put a 1 here, but in fact, you have to be careful, because, you know, what does having a 1 here mean? Okay, so let's just think about this for a minute. So if we've just got a group gamma down here and a group F here, to somehow say that, okay, we've got the finite quotients of gamma, that gives some completion of F. Okay? And what we're really saying is that completion is the same as the profinite completion. So why would that be true? And that's why you can put a 1 here. So that is true, that in fact the full profinite topology of gamma induces a full profinite topology on this free group here. Okay, so one needs to have something. So the full profinite topology is induced on F. And that's why this sequence is exact at the profinite level. Okay, so we know, that's the assumption, that delta hat is isomorphic to gamma hat. So we've got this extension now as well, coming from the fact that we've assumed n is fibered. So again, we have some guy g hat, where g is free of some rank. Okay, it's a fibered three manifold. The fiber here, because we've got no empty boundary, is a free group. Okay. The good thing here is that there's a unique homomorphism to Z. So this is something that we have yet to been able to get past. So these bundles have a unique maps to Z. So therefore, unique maps to Z hat. So these kernels must match up. So now we have a free group with the same profinite completion as a free group of rank 2. Now, just a billion quotients detects that. So this implies, so G free with G hat isomorphic to F hat implies G is a free group of rank 2. So then, of course, that doesn't necessarily mean that one's in the case of a once-punctured torus bundle, but in fact, because we're hyperbolic, one quickly gets to that point quite easily. Okay, so once you're a bundle, it's kind of easy to prove that you're free of rank 2. Now, if you weren't a bundle, and this is what has to be done in the case we want to rule out non-fibered, you just have some god-awful completion of something there that's just got the same finite quotients as a free group. And so that's an issue that, it's hard to get around, but it can be done. So, to handle the non-fibered requires a different angle. So handle non-fibered requires a different argument. And let me just say for the sake of brevity here that this also uses Wise's work on Lerf. It uses Pratitsky's Wise work on Lerf, and it uses Yield-Yu's recent work as well on separability of surface groups. So it takes a fair bit of machine to handle it. But let me just finish by making a couple of comments on this part 3 here. Okay, so comments on 3. Okay, so as Peter was mentioning, what does congruent subgroup property mean here? So we're in the world of out of F2, which we can think of as of GL2Z. And there are congruence quotients, as we were just describing earlier, that come from reduction mod integers. Now one can think of that as coming from Z cross Z and taking characteristic subgroups of Z cross Z. However, if we allow the following thing now, so instead of just taking very special characteristic subgroups of Z cross Z, let's take all finite index characteristic subgroups of the free group of rank 2. So let's let C in F2 be characteristic. So that's preserved in its finite index by all the automorphisms. And so this defines a finite quotient of C, of F2, and therefore we get a finite quotient out F2 to out F2 mod C. So from this perspective, we'll call a congruent subgroup of out of F2 something that contains the kernel of one of these things. So let's just say gamma C is kernel of phi, and say that gamma is a congruent subgroup if gamma contains some guy like this, okay? And it was proved. Now, again, GL2Z, as it stands, does not have the congruent subgroup when viewed as a linear group in the way we were just talking. However, Asada and others, and Richard probably knows better than I who else did this, but proved that out F2 has the congruent subgroup property. So all finite index subgroups look like. What's that?
They expand this
I don't think so. I mean, this would mean that all finite quotients would look like. So that's one.
What do these out F2 over C look like?
That's a good question. I mean, if you think about what characteristic subgroups of the free group of rank 2 are, you'll think, okay, abelian and nilpotent. And then I'll stop talking because it's kind of hard, I think, to kind of construct characteristic subgroups explicitly. I mean, Richard, no, it's. Yeah. I don't even know the dumb way, so. Okay, so the other ingredient that I mentioned there, which time is just about out, is this so-called omnipotence. So let me defer, saying what that is. What it means roughly is you can prescribe the orders of elements in finite quotients. Now that's obviously wrong as stated, because you could take an element and a conjugate, and you can't possibly prescribe orders. But if you take independent elements, then you can prescribe orders. That's kind of what the idea of omnipotence is. So how is this used? Well, you kind of assume that you've got these two bundles that are hyperbolic once-punctured torus bundles with monodromy phi and psi. And what you want to do, and this is enough to get the distinction, is to prove that there's some congruence quotient for which these guys have different orders. That's where you use omnipotence, and that's kind of where I'll stop. If people want to know about omnipotence, we can talk in private. Anyway, I'll stop there. Thanks.